Thanks everybody for coming, and thanks the organizers for having me. Like I said, my name's David. I'm from Sumo Logic, and we're going to talk a little bit about how we can do data science in kind of a private and secure way with some monads and kind of type-level programming techniques. So first, kind of word from our, I always say word from our sponsor, but this time it's literally true. We're helping sponsor the conference. Super excited. Yeah. So Sumo Logic, we are a machine data analytics platform. As you can see right there, it's right there up on the slide. We recently launched in Japan, so we actually now have an international site with that language, and I can kind of summarize it by piping that back through Google Translate, and this is what we get, actually pretty good. And as a matter of fact, I love this summary. We're going, how can you have data-driven insight to build, execute, and protect excellent apps in the cloud? So I'm sure a lot of you are building excellent apps in the cloud. So if you're looking for data-driven insight to build, execute, and protect that, you can talk with us. We have a booth over there. Of course, we're also hiring. And what that specifically means is kind of sending machine data to our service. So logs, metrics, and you can kind of analyze it, troubleshoot your system, check security things, everything like that. And so that's actually the context that kind of brings me to thinking about how we can do data science over some of this while maintaining some privacy and security around that data. So myself, I've actually been at Sumo Logic quite a while by our standards, 2011. Like I said, we're hiring. Of course, we're selling what we think is a great product. I also co-organize the Bay Area Machine Learning Meetup. So if anybody ever wants to do some Meetup Tech Talk or host a Meetup Tech Talk at your company, find me at this conference. Before that, I was doing machine learning research, and before that, I was doing a PhD. And a few weeks ago, can anybody know that? Can you guess the costume? Do you know who we are? Pua and Heihei from Moana. All right. So the talk, it's all pretty much there in the title. Privacy-aware data science. And what I'm going to propose is that I think data science and machine learning folks could be looking into more some of the information flow control literature from kind of the intersection of programming languages research and the security community. I'm going to propose how we can kind of use types as guardrails to maintain some security and information flow control. And if we kind of wrap all of that in sort of a monadic context, we get some of the benefits of a nice composable abstraction that engineers can understand and that other libraries can kind of interoperate with. That said, these ideas are absolutely sort of work in progress. I'm not going to propose that this is the final ultimate way to achieve all of this. I would encourage everybody to think of this as kind of a starting point. Hopefully you get to see some interesting ideas that kind of get your wheels turning. Maybe some useful references. And I think there's actually still a lot of open questions about how we can kind of best leverage type systems, functional programming abstractions, and things like this to achieve various guarantees and goals around maintaining privacy and security for data that we're doing data science and machine learning over. So previously, on Scale by the Bay, last year, I had the privilege to be a part of a functional programming for machine learning debate panel. And the question was, is functional programming the future of machine learning? And we were sort of randomly slotted into teams because given this conference, I think otherwise everybody would have just been on the yes team. I was actually on the no team. And we had to think of a line of attack. And it was data science notebooks. For the way they have the hidden state, they're very mutable. And this is what people love. These are kind of like dominating the market. And that was our claim. And the other side said that's a very bleak, pessimistic way to think about it. They sort of won over the audience, and we lost the debate. But I'm going to put an asterisk on that, because did we really? So if we look at 2018, notebooks are absolutely ascendant. This is to the point where they actually have a contrarian backlash in the form of a talk at JupyterCon this last year. So pure functional programming should be so lucky as to actually be having contrarian backlash talks at major conferences. That'll be a big milestone, I think. So pushing notebooks to production, data science with notebooks, all the cloud providers kind of pushing data science notebook as a way to get work done. So this is a really kind of key trend. And then, as a matter of fact, Sumo Logic is now a part of this trend. So we recently announced some data science notebook support where essentially we have some API level integration with a notebook running as a Docker image that can really easily get your data out of the service and interact with it in a notebook. And we're trying to kind of lower those barriers to adoption so that companies, data scientists or whomever, can do some interesting things with the kind of notebook workflow, notebook libraries on their machine data, their logs, their metrics, and things like this. So by all means, I would encourage you to check that out. But this adds some interesting concerns. And this is basically my talk proposal that I sent the organizers. What if you got sensitive data in the notebook, or you want to sort of be a little more careful? It's interactive. You're sort of iterating really fast. It's hard to have guardrails to make sure that you're not doing something you shouldn't be with the data, or letting data leak or bleed across boundaries or abstractions. And so there's kind of a threshold. Okay, you can just be careful. This is not really a solution. This is not really very scalable. And we're going to walk through how we can kind of try to do better and better by leveraging the type system, leveraging other pieces of technology. So that's the ultimate goal. Now the kind of roadmap here, we're going to talk about why the data can be risky, what we're going to try to achieve with it, what we're not going to try to achieve here, how this whole solution that we kind of walk through, and then why that's actually going to work and do something useful for you, be composable, and bring it back to the notebooks context. So who here knows who Clive Humby and Edwina Dunn are? All right, so their claim to fame was inventing the supermarket loyalty card program. So this is huge. Our entire kind of ad tech, surveillance capitalism dystopia, in some sense, we have them to thank for it. And they have this data is the new oil, right? And you've heard many remixes, data's electricity, data's all this other stuff. So another UK-based source, data is nuclear waste, right? And this is kind of in the context of breaches, personal information, security, all of these kind of concerns. So besides being something very powerful that we can do a lot of useful things with, you always kind of have to be mindful of some of the liabilities associated with data. And you have PII, you have various other kinds of financial data, medical data, everything like this. Many companies across a wide variety of industries, they have some data that's kind of free for all, and some data that they really want to be more careful with. And so, if you want to do data science, you need the data. And often you want to do data science over some of this more sensitive information. You need to explore it, clean it, iterate, wrangle, fit models, evaluate models, troubleshoot models, do this whole loop. And you're not going to do any of it without the data. And that kind of brings along these risks. Often, increasingly, we're seeing sort of a regulatory environment around data with GDPR and whatever the California version of that is called, I forget. As well as just companies, they're often trying to set an even higher standard than the regulation, and they have their own regulations. So there's a lot of reasons that you don't want to sort of be fast and loose with the data. Furthermore, there's also this notion of statistical contamination that we'll get to next. But you can actually sort of get yourself in trouble from a machine learning quality perspective if you're not careful about how data is flowing through your machine learning pipeline and workflow. And so notebooks just kind of put all of this on steroids. I mean, the interactivity, the quickness, you can sort of make mistakes and do things sloppily quicker than ever as well. It's definitely a double-edged sword. So this really becomes an interesting question in the data science machine learning community. So this is like a modern classic paper. I would absolutely encourage you to take a chance and read it sometime. And it actually won the best paper at KDD 2011. And what they look at is a lot of these kind of data science competition, Kaggle-like things, and look for what they try to characterize this phenomenon of leakage. And a lot of people who have done machine learning in practice can tell you sort of various horror stories about this. In the paper example, they actually have a medical one where you're trying to predict patient outcomes. However, the patient ID was sort of correlated. They were issued sequentially, and they were correlated with what facility the patient was at. And one of the patients, or one of the facilities rather, is actually hospice care. So the prognosis for those folks was generally not great. And you could use that to really get accurate predictions, even though that had nothing to do with the medical prediction task as such. You're sort of cheating. And in production machine learning systems, you're usually just cheating yourself if you have that kind of leakage. Another example sort of you can think of it, you can imagine that Salesforce, they've got a bunch of great talks here this year. Maybe they're trying to predict which sales leads are going to close, but they have a field in Salesforce that only gets populated when the lead closes, right? Like contract signing date or something. And now if you just dump all of this kind of oblivious into your machine learning workflow, having any value at all in contract signing date is going to be a great predictor of leads that close. But you really haven't done anything useful. And this paper is actually interesting. What they propose is something they call like legitimacy tagging. And they don't really get into the mechanisms of how this might work, but they just talk about conceptually, what fields, what parts of data are like fair game for the machine learning and what are sort of protected or restricted. And actually, again, back to Scale by the Bay last year, our erstwhile debate nemesis from the other side, Oscar, actually did a really interesting talk about machine learning and feature engineering. And this talk basically had a kind of functional reactive feature engineering technique for event streams to achieve what Kaufman et al. In the paper called no time machine. And basically, the idea here is, again, the issue with that contract field in Salesforce, this hypothetical thing, is that it's information from the future that's not really, you shouldn't have when you're trying to make predictions. And by deriving sort of a declarative functional feature engineering technique from the event streams, they can kind of eliminate by construction this sort of time travel problem. And anybody who does kind of hedge fund, quantitative finance, this kind of stuff, they're also constantly plagued with how do I avoid the time travel cheating. So these are cases where not for just sort of privacy, sensitivity, security, but just for the quality of your machine learning, you really want to be careful about how data flows in your program. So what are we not going to care about in this talk? Cryptography, right? We're just going to assume the data is encrypted, it's handled securely, all of the data is done in the clear. If you sort of search around for machine learning and privacy and security and things like this, you'll find a ton of really cool resources about how you can do the machine learning on the data while it's encrypted and homomorphic encryption and things like this. But we're going to table that for now. By the way, that car is like a block from my house. I saw this. Oh my gosh. All right. That's San Francisco crypto lifestyle here. Also, not a goal right now, or not a tool that we're thinking about, but it would be interesting for you to know about, is differential privacy. This is a Gödel Prize winning stuff. Cynthia Dwork and others kind of work on this, and it actually very, very interesting and principled approach to this that has some very high-profile adopters. If you actually search for Apple in this, you can see the Apple white paper about it. The Census Bureau is talking about it. It's kind of they pose it as sort of a computational, a very kind of formal definition of what it means to be private in aggregate. Again, not going to talk about this. We could eventually imagine composing this with the sort of techniques we are going to talk about. Also not in scope are actual kind of malicious adversaries. So this is, a lot of the research and the papers I found about this were sort of Haskell oriented, and they could make these kind of absolute guarantees about security and absolute, you cannot do this, programs will not be able to do that. On the JVM, there's sort of a side effect backdoor in almost anything you do ever. And so if somebody is actually writing code against your data, they can always do things like just write it out to a mutable variable or something. Or this absolute top-notch exploit right here. If you run this in Scala, you can, for the most part, you'll get what you want. So this is also something we're not concerned about. We're not trying to actually protect the data from hackers or anything. We just want to give engineers tools to help them do the right thing more easily. Furthermore, we're not looking to replace an actual organization level commitment to responsible data handling. So this is our compliance and data protection officer, or I guess this is the assistant to the compliance and data protection officer at Sumo Logic. So the actual employee her name is Jen. This is her dog Max. But there's all sorts. Anybody who's kind of worked in an organization where data security and privacy is taken really seriously knows there's tons of procedures, thinking, procedures for the procedures, monitoring of the procedures, auditing of the monitoring of the procedures, and so on and so forth. So if you tell your PCI auditors that you have a monadic type-safe layer and kind of clap your hands and walk away, it's not a great idea. So this is absolutely not a silver bullet for these kind of things. It's just kind of one more tool in the toolkit. So what we do want to do is do useful work with the data, but don't allow kind of direct access to the sensitive data or unintended information flow of that data. And the real question, how can computers help us do this? This is why we have them, right? And the actual approach, this is a kind of a requirement sketch. What I would like to have is my data in an imaginary box. And when it's in that box, I cannot directly access it, I can manipulate it in place. I can desecure it, but only in specified controlled ways that kind of go through some auditing or some review. And you can sequence those transformations and mix and match them, and the security level will be set by a last write wins. So walking through that in a little more detail, it's in the box. You cannot directly access it. There's no .get. You can manipulate it in place. And so, functional programming enthusiasts will already kind of see what's going on here. I have the data in the box. I have a function. I want to apply the function to the data in place in the box. Get a new box with the result of that function inside. I can desecure it. Likewise, functional programming folks probably can see some patterns. This is, I want to transform the data and simultaneously, as a side effect, change the strength of the box. So now it's maybe a box that I can get the data out of. But maybe I do another analysis where I pull in some other data from a secure source again, and now the data is once again back in the box. And so I want to be able to kind of compose pipelines of these data transformations and basically classify, declassify side effects and achieve this. So if we kind of look at all of these and kind of box them out, we can sort of map these to some ideas that we know and love from kind of Scala and functional programming, right? So we have the box, it's kind of this container type, this parametric type, and you can't access it directly, but you can map a function into it. This is like a functor, and you can process it in this pipeline sense, and you can mix and match these processing sequential steps, and this is like a monad flat map in the Scala parlance. So let's dig in a little bit more, and there's actually all of this idea kind of comes from a research paper that I found searching for all of this stuff. So when I kind of searched, I figured we had these requirements, we had these needs, and I figured somebody else had thought of this stuff before, and a lot of people had. In some sense, this was one of the few ones I could understand. This is kind of this one was within my range of being able to parse what was going on, at least somewhat. And what they propose is this kind of monad wrapper layer, where S is sort of the level, and A is the type of the internal data. So this is that they implemented in Haskell. The paper is in Haskell. All of the papers for this essentially are in Haskell. But basically, this is a container type with two type arguments. One that says what is the level, high security, low security. We'll get to that in a second. And the other one, what is inside the box. And so the levels. So this is the lattice model of secure information flow. And this woman who sort of invented this in 1976, side note, also did the early work for the theory of modern intrusion detection at SRI in the 80s. So this is a really interesting idea where we're going to define a formal model of how these security levels interact. And then the idea is you have some mechanisms that enforce the model. And what is a lattice, and why is this a good way to think about it? So there's a whole lot going on here. It's basically just an ordering relation, a partial ordering relation over your security levels. And the idea is that if you're lower, you do not allow higher data to flow to the lower level, but you can send lower data to the higher level. And that's the partial kind of ordering sense. A lattice just means that all pairs have a unique greatest lower bound and least upper bound. And what this means is that given two pieces of information, I can sort of compute a lowest common denominator level that if I merge the two pieces, that's what it should be. In the original paper, they kind of do this with subset just to motivate it. But the real key takeaway here is this gives you a mechanical way to determine whether code X at level X can read data at level Y. And if I combine data at level A and B, what is it? What's the resulting level? And intuitively, the resulting level is sort of the lowest level that covers both of them, that's higher than both of them. So you don't want to let data be desecured by combining it, but you sort of have to find that common ground. So one kind of difference for how we're going to do this versus the paper is this SecLib paper defines a monad family. So you have one instance per level. And you can kind of map and flat map within this, but they're only connected via these explicit transformations. So it actually, the paper out of the box doesn't have our like classify, declassify effect that we're looking for. So we kind of tweak it a little bit. We want basically last write wins join. So if this is the Haskell type signature of what the join would look like, you have a secure wrapper around another secure wrapper, and the inner one is sort of the last write. And so when we join, we want the inner one to kind of quote unquote win. So if we sequence a whole pipeline of actions, they become nested flat maps, which you can equivalently think of as these nested joins. And the very last action, wherever we end up, that should be the final result. This doesn't exactly work out. I'm not going to dig all the way into this, given the way that it's implemented in the paper. Basically, we have to add an identity element, a neutral security level. So certain operations are just saying, I don't really care about changing the level. This, if I combine neutral with anything, you get that other thing. And now that you have an identity, again, kind of stepping into some of these concepts, you have a non-commutative monoid over the security levels. So I can combine any two security levels, and there's an identity element that combined with level high gives you high, combined with level low gives you low. Again, for the lattice theory from the Dorothy Denning paper, you could have these very, very rich security lattices for our purposes, and in the SecLib paper, we just say there's high and there's low. So it turns out that kind of tweaking it in this way is, in some sense, equivalent to accidentally reinventing this other thing called graded monads. So this is actually credit here to Professor Russo from the SecLib paper. I emailed him some of my questions, and he said, oh, what you're actually talking about is this. And I went to those papers. They looked fascinating. I could not understand anything of what was going on in those papers. You can check it out yourself. I'm sure it's very interesting work, but I really couldn't parse it. However, Professor Russo was kind enough to kind of give me the summary that it's basically a family of monads indexed by monoids. So here, again, we have the monoid of the security levels. We can combine security levels and kind of hop, skip, and jump across the monads. And in this case, the join, another way to think of it besides last right wins would be this like join has this least upper bound. And this is kind of back to the Denning idea. But what we're going to do is we're going to do last right wins. And in order to make that work out with the monad and applicative laws, we had to add a new security level called neutral, and this is fine. So this actually achieves our goals. So now we have some conceptual design for this data wrapper box that sort of does what we want. And the next question is, okay, how do we actually code this up, right? So we have the idea, we have the theory, we have some Haskell snippets. Now we want to implement it in Scala. So the attempt 0, and if folks have some better idea after, I just rewrote the Haskell code directly in Scala. And actually it did not really do what I want, in some sense because I couldn't pattern match on this like other type argument. If folks who know more about type tags and such than me want to talk after about how this could have been done, I would love to hear it. But this, I play around with it for a little while, cannot make it really do what I like. So next one, I just say we're going to value encode the security level. So we just create a sealed trait, some type over the different security levels. And then that kind of gives us a straightforward way to implement flat map. Here we go, that basically if you have the neutral, you get the other level, and otherwise you get the last right wins inner level. And then the reveal method, which is sort of outside the monad API, but part of the security API, is we're going to say, when I want to get the data out, if it's at the low security level, it's fine, otherwise it's not fine. And for this scheme to work, the important thing is that by kind of, again, we're not protecting against hackers, we're just trying to help engineers. By convention, you want to have only sort of pretty reviewed and trusted code actually owning the ability to write data at the low level in a flat map call. So you sort of fence off your API or your library design in some way that you have sort of reviewed and audited code that can declassify high classification data, and you have other code that just kind of consumes it. And as long as you kind of maintain that boundary engineering-wise, you don't really have to worry that other code is going to accidentally reveal the data. In the Haskell SecLib paper, they make this demarcation between trusted and untrusted code, and they have some stronger guarantees, again, because it's Haskell. But here we're just going to say, organizationally, if you kind of do this, you should be OK. So can we push this into compile time? This is the kind of type level thing. So this is the truth table for how we think about the monadic join, right? We have the outer type, the wrapper, and then the inner type, this last right wins, and we have what we want the result to be. Assuming that the functions that are constructing instances of our security wrapper output fixed and static levels, we don't have data-dependent processing here, this is what we want, right? So how can we do this? I would encourage you to check out this awesome presentation by Stefan Zeiger about type-level computation in Scala. He has a really, really nice example with Boolean, to build it up the way that I think about it after reading his presentation several times. The trick is you have an abstract type associated with a trait. So you have the trait, you have some abstract type in it. You actually make it take a parameter. We're going to make this be, ultimately it's an endo function. It's going to just map back into itself. So we're going to add a subtype constraint that the type argument to this type is itself a member of the perm. So perm is going to be permutation. You have some instantiation. So in this one, we're going to say we have red, green, and blue. And they're all extending that trait. And they all have this abstract type member. And the abstract type member, remember, it's going to take a type argument that is also a permutation type and return something. Okay? And now we can actually encode a permutation or a bijection onto itself by just supplying the type arguments to kind of fill this out. So by this trick right here, actually at compile time, all of the sort of type annotations kind of flowing through your program, the compiler is going to be able to evaluate, okay, given this type here, this concrete type here, supplied with this argument, I can thread it through and compute what that argument should be. And leveraging this kind of machinery, we can kind of combine it with our idea for how we want the privacy layer to work to prevent unsafe data access from even compiling. So taking that truth table and boiling it down to something much simpler, we can say the inner type, when it's neutral, we're going to just accept whatever the outer type was. When it's low level, last write wins. And when it's high level, last write wins. The inner type is sort of the last guy in that monadic pipeline. It's the final security operation. That's the winner, unless it's neutral, which is this thing that we want to kind of make a lot of operations work out and make sense. And in this case, we're also going to encode what we want with revealable, which is going to be another trait defined only over the security levels that we are kind of comfortable exposing the data as. So we kind of take that same trick from the permutation stuff we just talked about. We're going to basically say that any privacy level has this outer that takes an argument that's the outer guy in the monadic join, and it's going to return a privacy level type as the result. And this type constructor in the abstract type member of our security level acts as like a type level function. It's all evaluated by the compiler at compile time, and it's going to output the result of what the monadic join should be for this level. And so that's kind of the way we would implement the trait itself. Now how we actually use this in the function, again, we have the revealable low always wins, last write wins, high last write wins, outer differs to the other guy. So the actual join type signature ends up looking like this. And we can kind of define flat map in terms of join. Given the way we're talking about last write wins, for me it was a little more natural to implement join. Okay, so there it is. But let's break down the components. So we have the outer level, which is a privacy level outer, privacy level inner. And we have the argument to the monadic join, which is a double nested security, which is basically, again, sort of the result of what you get in the flat map implementation. And we want the output to be a single nested security wrapper with the target level that we want. And you can see that by sort of this hashtag kind of operator guy, we're able to access the type member of the inner security level and then send the outer security level as an argument to the type level function contained there. And that becomes the type of our result. So this whole thing just kind of happens. And now we get the result we want. And what this happens is that if I have an aggregate operation that does something sensible and reasonable, basically this takes a string. So aggregate is the kind of function you might have in your sort of controlled library. It's going to take the string and compute the length. Now the string is gone. This is very simplistic. And you just have a number. So maybe we say this is OK from a privacy and data leakage point of view. And it returns the length wrapped in a low security wrapper. And so and you can do this in Scala test, which I found out in the process of doing this that I didn't know before. You can actually supply a string to Scala test and say, does this string compile or not? And so that's actually kind of a cool trick. But you can see that if we say reveal on the high security we just map. So again, we do the functor fmap and say underscore length Okay, now we have a high wrapper around a number, but you can't unwrap the number because we didn't declassify. We didn't have the monadic effect from a flat map to change that security level. So just simply kind of functor classic map of the length function is not sufficient to allow us to access the data, but this special approved aggregate function, because it wraps the result in the low security, it actually essentially has the monadic effect of declassifying your data. And that one does compile. So that's it. That's what we kind of hope to achieve, right? And now why? Why do we do this again? Let's circle back after kind of diving into the Haskell to Scala translation and type level functions, resurface to kind of think about the context of why we would think this is useful. So again, we're in the data science notebook, and you want to really explore and iterate and play with your data really quickly. But we don't want to accidentally pull data we shouldn't, look at data we shouldn't, combine data in ways that we shouldn't, or likewise, let data from the future leak, let data that has sort of features or side channel information for our data science problem leak across those boundaries. So we want to just kind of have the freedom to not worry about that while we're interactively hacking in a notebook. And so we outsource that thinking to this kind of wrapper library layer. And again, if by kind of convention and organization, you have the code that is capable of unwrapping under some more stringent path, maybe different reviews, different audits, things like this, then you can interactively hack to your heart's content and not really worry about that leakage. The machinery is going to kind of make sure that you're, in some sense, doing something reasonable here. So that's the big idea. And why kind of do this when I was looking through all sort of the related work and the research, why do this with monad and functor and everything, and why worry about if the laws work out? You know, there's another thing you could do. You could do what's down there. You could have a secret object that you say .update, and you pass a function, and now it changes in place. You could say .set the security level, and now it does this. You could .get and get it out. Now that said, it's not really going to be. I guess you can read it and sort of understand what it does. Maybe it's a little. It's got that, I guess. But it's going to be really hard. It's kind of a custom API. People are going to have to kind of wrap their head around what's going on here. It's not, in some sense, in the functional side, it's going to be a little more standardized. And also, this is going to be very hard to compose, right? Like, you're not going to really be able to reason about what's going on. At any given time, the compiler just knows, I have a wrapper thingy. It's not going to track the type information. It's going to be really challenging to make anything reject anything at compile time. So we get a lot of benefits the other way. Engineers can understand it, other code can interoperate with it. And so sort of an example, and again, just to bring back, this operation is map or f functor map, right? This operation is, the effect is sort of flat map or bind or something like this. So again, if you kind of are familiar with these concepts already, the security thing should make a fair deal of sense to you out of the box. And then finally, let's say that we want to construct a privacy-aware data pipeline for our notebook hacking, right? However, some operations may fail and return no result. Oh boy, if only there was some Scala language construct that could handle an operation that fails and returns no result at all. So let's walk through this. So say that this is our pieces that we're building our little example out of. We get a query from the user, from something. Maybe it's there, maybe it's not. We get the user data. It's going to return a monad transformer of option and the security layer. We can analyze the data and return a low security layer. We can do a leaky analysis that still returns a high security layer. And then we have a reporter that just takes a string and gives you takes a double rather, the result of the analysis, and outputs it as a nice string. And so how do we string all these guys together? Okay, we can kind of put it all in a nice for loop that we all love, or the for comprehension. And so we can sort of lift the option target query into a monad transformer option and security. We can get the user data, which is already going to return an option security monad transformer. We can lift the results of the analysis into the same structure, and we just yield the result, and we have a nice doubly wrapped thing. At any given time, if the security does what it does or doesn't do, and the option, these effects interact natively, option knows how to make security, security knows how to make option. Everything, quote unquote, just works. This is done with the CATS library. And so that's an advantage of implementing the security layer in these kind of standard formalisms, this monad kind of stuff. And you can imagine if we have a different one, a leaky one that keeps it at high or low, again, we'll get the result we want. Everything will just work. We can kind of plug and play these pieces. All right, so some question for future work. I'd love even better way to do it in Scala, especially if folks know type tag. I'd be interested. Are there use cases for richer lattices? I'm not sure. Could we do data-dependent declassification, like differential privacy? Well, I'll do question in 1 second. Again, I think there's a ton of cool ideas in information flow control and PL security research that could be used for machine learning and data science. Could we use property testing for anti-leakage? And there's a whole new kind of machine learning area of like trustworthy AI about how we can build kind of tamper-resistant AI and machine learning systems that I think these programming language ideas could be really useful for. So that's the big picture. Thanks again for listening. I'd love to take any question if we have 1 minute.
We have a few minutes for questions. First, thank you, David. It's great to hear these kind of algebraic solutions to problems that are usually just solved more communally. But I don't have a mic to hand around, but are there any questions?
This is good.
So it seems like it works when one security level can sort of contain another security level. Have you thought about how this works when group 1 can see fundamentally different things from group 2, and sometimes they might overlap and you want that fine-grained control?
Yeah. So, yeah, that would be like the lattice stuff. Like hypothetically, you should be able to encode that in like the richer lattice model. This implementation just kind of does low-high, and maybe you'd have like a more complex truth table. But you should be able to encode. The whole idea of the lattice is that's always well-defined. If you define a lattice over security levels, you always know how to combine them. There's always a truth table as long as you do that.
Great stuff.
Cool.
Any further questions? No? Then thanks again, David.
All right, thanks.
Wonderful. And we'll start our next talk.